Imagine an AI agent that scores exactly 33.3% higher on the absolute hardest real-world benchmark tasks out there. And get this, it doesn't do it by relying on some massive new foundation model. No, it simply and safely rewrites its own source code and tools on the fly, completely without human intervention.
Welcome back to the hidden layer, decoding artificial intelligence. Look, if you're building AI applications today, here's my 30-second promise for this explainer. We are diving deep into a groundbreaking new research paper on the Autogenesis Protocol. We're going to show you applied engineers exactly how to build verifiable, self-improving agents that actually survive in production without completely breaking down. But right out of the gate, this raises a massive technical headache, right? I mean, how on earth does an autonomous system change its own code, tweak its own prompts, and rewrite its own tools without instantly corrupting its memory or just nosediving into a death spiral of errors? Well, stick around to the very end of this explainer because I am going to reveal a specific secret, the commit operator, that guarantees these self-modifying agents stay perfectly stable. Okay, so here's our roadmap for today. We're covering the brittle agent problem, the Autogenesis solution, the two-layer architecture, the self-evolution loop, some real-world proof, and finally, the dawn of the protocol engineering era. Let's jump right in.
Section 1. The brittle agent problem and why static designs fundamentally fail.
Let's talk about the absolute core pain point every single applied AI engineer is feeling right now. The traditional way we build LLM-based agents, it's just entirely mismatched with reality. We're currently stuck with these static agents built on brittle glue code, monolithic architectures, and manual updates. We hard-code prompts, we tightly couple tools right into the agent's logic. But the real world? It demands systems that can handle stochastic, totally unpredictable environments, systems that require dynamic adaptation and traceable evolution. When you try to just slap self-modification onto a static system, you end up with a completely unauditable mess. Without explicit lifecycle management, self-modification literally introduces massive runtime instability. It is an absolute recipe for disaster.
Section 2. The Autogenesis solution, or decoupling evolution. To escape this trap of endless brittle hacks, we really have to elevate our development into a rigorous, formal protocol. Enter the Autogenesis Protocol, or AGP for short. Now, the researchers define this as a standardized self-evolution framework, but the real magic is in the second half of that idea. It strictly decouples what evolves from how evolution actually occurs. Just think about that for a second. Instead of hard-coding evolution straight into the agent's brain, AGP creates a formal standard. The underlying resources are completely separated from the evolutionary optimization logic. This ensures that when the agent evolves, the whole process is modular, traceable, and, most importantly, completely safe. This is how we finally build truly verifiable AI agents.
Section 3. The two-layer architecture, featuring RSPL and CPL. Let's see how it actually manages this without breaking.
This architecture brilliantly separates concerns, specifically when we look at the AIGNE implementation framework. On one side, we have Layer 1, the Resource Substrate Protocol Layer, or RSPL. Here, things like prompts, agents, tools, environments, and memory are all modeled as passive protocol-registered resources. They don't have optimization logic secretly hidden inside them. They are version-controlled entities with explicit, clear lifecycles. Then on the other side, we have Layer 2, the Self-Evolution Protocol Layer, or SEPL. This is your control logic. Because Layer 1 treats everything as a standardized object, AIGNE allows Layer 2 to seamlessly apply optimization algorithms across literally any of those components. It's just a beautiful, clean architecture designed for real-world engineers.
Section 4. The self-evolution loop and iterative improvement. Let's take this from theory to an actionable application.
So this is the SPL evolutionary loop in action, exactly as the AGNE framework implements it. And to be clear, this isn't just heuristic guessing, this is heavily grounded in control theory. Step 1 is reflect. The AGNE-powered agent analyzes high-dimensional execution traces to pinpoint specific causal failure hypotheses. Step 2 is select. It translates those hypotheses into concrete update proposals, like, say, realizing a sorting algorithm is too slow and then proposing a fix. Step 3 is improve. It applies those discrete updates via the standardized RSPL interfaces to create a provisional candidate state. Step 4 is evaluate. It rigorously tests this new candidate state against the original goals and strict safety invariants. And finally, Step 5 is commit. We are going to talk more about this crucial final step in just a second, but this strict loop right here, this is exactly what converts messy text modifications into rigorous, verifiable engineering.
Section 5. Real-world proof. It's time to test the agent. Theory is great, but we need the hard data to prove why this is such a game changer.
The data from the Gaia benchmark brilliantly illustrates the sheer power of Autogenesis. Gaia tests real-world, multi-step objectives demanding complex planning and tool use. Now, on the absolute hardest tier, level 3, a standard vanilla agent achieves a 61.22% success rate. Not bad, right? But the Autogenesis system, specifically utilizing its evolved tool capability, rockets that up to 81.63%. That is exactly a massive 33.34% relative improvement. By dynamically creating and refining its own tools on the fly, the agent completely bypasses the bottleneck of a static, hard-coded toolkit.
But wait, it actually gets even better. When you look at the trajectories on algorithmic coding benchmarks, evaluating languages like Python, C++, and Java, the gap between the evolving agent and the vanilla agent actually widens as tasks accumulate. This is huge because it proves that self-evolution is not just a one-off parlor trick. The agent is continuously experiencing compounding improvement. It actively finds its own failure modes, patches them up, and just gets exponentially more efficient and correct over time.
So, let's close that open loop I promised you earlier. How does the system do all of this without totally corrupting itself? The secret is the commit operator. Back in step 5 of that evolution loop, the commit function acts as a ruthless conditional gating mechanism. Because every single resource is strictly version tracked by layer 1, the commit operator can thoroughly evaluate any proposed update against absolute safety invariance. If an update fails, or honestly, if it just doesn't strictly improve performance, it doesn't crash the system. No, it instantly rolls back to the previous stable version. It guarantees monotonic improvement. Bad code is literally never committed to the active state. And that, my friends, is the ultimate key to verifiable AI engineering.
Section 6, the protocol engineering era, and our new paradigm. Let's zoom out and look at the big picture.
The researchers state this paradigm shift perfectly, calling it a potential shift from manual prompt engineering to automated protocol engineering. I mean, just think about how many hours we currently waste tweaking prompts, writing fragile glue code, and manually adjusting tool parameters. Autogenesis moves us entirely beyond that. By equipping our agents with standardized self-repair and evolution capabilities, we are actively building the foundational paradigm for next-generation agent networks that can actually sustain autonomous adaptation in incredibly complex environments.
Which leaves us with one final, incredibly important question. Are you ready to stop writing brittle glue code and start engineering self-evolving protocols? The research is crystal clear on this. The future absolutely belongs to systems that can safely and autonomously adapt. So let me know how you plan to implement the Autogenesis protocol in your own stacks down in the comments. And hey, if you found this explainer valuable today, make sure to hit subscribe to The Hidden Layer so you never miss out on decoding the systems that are actively shaping the future of artificial intelligence. See you next time.